All right, this is our lesson on rates of change. So we'll start off by talking about the average rate of change between any 2 points on a graph of f of x. It is just the slope of the line through those points. So notice that a parabola here does not have an actual slope. The average rate of change, if I connected those with a straight line, we find that slope. So average rate of change, or AROC, you subtract your y values over subtract your x values, just like slope. We find the y values of the function for the given interval, and then just find the slope between those 2 points as if it's a straight line. So let's find the average rate of change for these two functions on the intervals given. So the first step we do, we find f of -2 and f of -1. All right. Well, -2 gives me -2 cubed plus 3 times -2, which is 8 minus 6, which is 2. And f of -1 is -1 cubed plus 3 times -1, which is +1 minus 3, which is -2. Then we just find the slope between the 2 points, -2, 2, and -1, -2. So our slope is subtract my y values over subtract my x values. So I get -4 over 1. Our average rate of change is just -4. Same thing for the second one. We'll find h of 1, which is 1 plus 1 over 1 plus 6, which is 2/7. And we'll find h of 4, which is 4 plus 1 over 4 plus 6, which is 5 over 10, or 1/2. This one's going to be a little bit more complicated because we have fractions involved, but that's okay. Our 2 points then are 1, 2/7, and 4, 1/2. So we find our slope by subtracting the y values, so 1/2 minus 2/7, over subtract the x values, 4 minus 1. In order to subtract these fractions, remember we need a common denominator. So I will make that common denominator 14. So we have 7/14 minus 4/14 over 3, which gives me 3/14 over 3. Please never leave a fraction within a fraction. Think of it as dividing by the denominator. And to divide by a denominator, we multiply by the reciprocal. Those 3's cancel, leaving me 1/14 as my average rate of change. There we go. This time we have a graph, and I want the average rate of change of the graph of this function on the interval -1 to 3. Well, we start out the same way. I need 2 coordinates, -1, comma something, and 3, comma something. I just use the graph. -1 has a y value of 0. 3 has a y value of 4. Now I just find the slope between those 2 points. Or I could look at the graph and connect those and find the slope that way. But I like the math. 4 minus 0 over 3 minus -1, which is 4 over 4. This has an average rate of change of 1. And then we also have a table. The table above lists the life expectancy of U.S. females born in a given year. We want the average rate of change in life expectancy for U.S. females born from 1850 to 2000, include units of measure. This time our points are given to us. We just have to look. 1850 and 2000. Those are our points. Now we find our slope. Subtract the y values. So 81.83 minus 46.10 over subtract the x values, 2000 minus 1850. All right, I'm going to use a calculator for this one. 81.83 minus 46.10 is 35.73 over 2000 minus 1850 is 150. And then we divide 35.73 by 150. We get 0.2382 units of measure. Well, this is years of life expectancy over year of birth. So you gain 2.2382 years of life expectancy per year born, we'll call it that way, per year later that you were born. So if you were born in 2001, we would add 0.2382 to that life expectancy. I'd expect you would live about 82 years. Can we find instantaneous rate of change? That means rate of change at the exact moment in time. The idea of instantaneous rate of change is equivalent to finding the rate of change of a function at a given point. This concept is developed formally and used in calculus, but we can approximate the rate of change at a point by using average rate of change over very small intervals. So a ball is thrown vertically in the air. For t being between 0 and 5 seconds, the height of the ball is modeled by this function, where h is measured in meters and t is measured in seconds. Find the average rate of change in the height of the ball over the following intervals, including units of measure. So in order to find the average rate of change on this first interval, 1 to 1.1, we need h of 1, and I'm just going to use my calculator to do this. Let me show you a very fun, quick way to do this. If you go into y equals, clear whatever's in there out, and type in your function, negative 4.9 x squared, obviously we have to use x instead of t, plus 25x plus 5, then quit. I can find h of 1 very quickly by hitting alpha trace. I put my function into y1, so I'll put y1. Then in parentheses, the value I want to evaluate at, and there's h of 1, 25.1. h of 1.1, I do the same exact thing. Alpha trace, y1, and then 1.1. I don't have to re-enter the function because it's saved as y1. I get 26.571. So my average rate of change is 26.571 minus 25.1 over 1.1 minus 1. I get an average rate of change of 14.71. Then I do the same thing on my other intervals. H of 1 is still 25.1. H of 1.01 is 25.25151. I find my slope by taking 25.25151 minus 25.1 over 1.01 minus 1. So 25.25151 minus 25.1, and divide that by 0.01. We get 15.151. Then I'm going to find it on an even smaller interval. H of 1 is still 25.1. H of 1.001 is 25.115191. And I'm going to find my slope by taking 25.115191 minus 25.1 over 1.001 minus 1. Another trick for this. Instead of typing in this entire decimal each time, I can just hit second answer, minus 25.1, and then divide by 0.001. And there we go, 15.1951. And then our last one, we would need H of 0.999. $25.084, blah, 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 blah. We'll call it an 8. And I still know H of 1 is 25.1. So my slope is 25.1 minus 25.0848 over 1 minus 0.999. It's a good idea to definitely use the answer if I was rounding a number in here, because you don't want to round anything until the very, very end. So I want to make sure I use that answer key this time. I get 15.20 4, 9. So based on this example, what do I think the true rate of change is at exactly 1 second? Well, my values coming in were about 15.2. I would say it's probably about 15.2. And I did forget something on all of these. It said include units of measure. We have meters and seconds. So these are all in meters per second. So my estimate is that at t equals 1 second, the ball was moving 15.2 meters per second. So the rate of change of a function at a particular point is the rate that the y values would change if the x values changed at that point. This concept is what we call instantaneous rate of change later in calculus. While we cannot find the rate of change at a particular point in AP Precalculus, we can do the following two things. One, we can estimate the rate of change at a point by finding the average rate of change over a very small interval. And two, we can estimate rates of change at two different points by estimating individual rates of change using the concept of a tangent line. Remember, a tangent line is a line that only touches our curve in exactly one place. Note, when we discuss the rate of change of a function, we are essentially discussing the slope of the graph. If the graph of f has a positive rate of change, then the graph of f is increasing. Likewise, if the graph of f has a negative rate of change, then the graph of f is decreasing. So at this point, we are going to find if the two quantities have a positive rate of change or a negative rate of change. So as one goes up, is the other going up or down? A child's age versus the child's height. Generally, the older you are, the taller you are as a child. So this would be a positive rate of change. A golfer's skill level versus the golfer's score. Well, as your skill level goes up, your score tends to go down in golf. So this is a negative rate of change. And the height from the ground of a coin dropped off the Burj Khalifa versus the speed of the coin as it falls. This one's a tricky one. So the height from the ground of the coin and the speed are actually, the height is decreasing and the speed is increasing. So that's actually a negative rate of change, because as your height goes down, your speed goes up. Estimating rate of change at a point, the graph of f is shown along with the tangent line to f at x equals -4. In calculus, we will learn that the slope of the line tangent to the graph of f at any given point is the true rate of change of f at that point. And in calculus, you learn ways to actually solve that. While we cannot find the slope in AP Precalculus exactly, we can sketch the tangent line and estimate the rate of change. So this is my tangent line. It touches it in exactly 1 point. I can estimate that the slope of this line is about 1, 2, 3 over 2-ish. That's the idea. So let's estimate the rate of change of f at x equals -4 using the slope of the line tangent. Oh, that's the one we just looked at, right? So I pick another point that's on my line, and this one's about here, so 1, 2, 3 over 2. My rate of change is about 3 over 2. That's definitely not exact, all right, but it's close enough. Let's sketch the tangent lines at these 5 other points. Well, 4 other points. We've already got this one. So sketching a tangent line is just sketching a line that touches at exactly that 1 point. So if I sketch a tangent line here, probably going to go below, and that's about my tangent line. So you're just doing your best to only touch it 1 time. This one at the bottom of the curve is nice. That's a horizontal line. And then this last one, I probably want to be on the outside here. The steeper it is, the harder that tangent line is to draw, really. All right, does the graph of f appear to have a greater rate of change at x equals 4 or x equals 5? Oh, I missed one on that last one. I apologize. Man, I missed this one. So now when I ask if its rate of change is greater at 4 or 5, 4 or 5, well, which one has the steeper slope? At 5, it has the steeper slope. So the rate of change should be greater at x equals 5 because the tangent line has a steeper slope. And there we go. Connecting rates of change of f with the graph of f. If the rate of change of f is positive, then the graph of f is increasing. If the rate of change is negative, then the graph is decreasing. We also have concavity to talk about. Remember, concave up is when it opens upward like that. It would hold it like a cup. Concave down is the upside down version. It would not hold water. If the rate of change is increasing, then your graph is concave up. If the rate of change is decreasing, then the graph is concave down. So the graph of f is shown not above, it's actually below on my picture. We're going to describe the graph of f and the rate of change of f. There we go. The graph of f is, well, increasing or decreasing. It is going up left to right, so it is increasing. And it is concave, well, it would not hold water, so it is concave down. Because the rate of change, well, the rate of change is positive. And it's concave down because the rate of the rate of change is decreasing. If we look at these tangent lines, right, here we got a positive one, right? Here it's still positive, but it's definitely less than it was further to the left. Be careful when answering questions about graphical behavior. Pay close attention to the wording of each statement. Does it refer to the graph of f or the rate of change of f? Be very, very careful. So we have some pictures, and we're going to circle the best word. So in this first one, the graph is positive or negative. Well, it's all above the x-axis, so the graph itself is positive. The graph is increasing or decreasing. Well, my y values are going down, so it is decreasing. The rate of change, well, if I look at any of my tangent lines, those are all negative slopes, so the rate of change is negative. The rate of change is increasing or decreasing. Well, if I look at this, that slope and this slope, well, it's less steep, but remember with negative slopes, the less steep is actually a larger value. So the rate of change is increasing because this might be a slope of like -3 and this would be a slope of -1. Why not? That's actually an increasing value. So be careful with those negatives. All right, second one, the graph is positive or negative. It's all below the y-axis, so it is, it's all below the x-axis, so it is negative. The graph of g is, well, it's going up, so it is increasing. The rate of change, if I look at any of my slopes, those are all positive. Remember, positive and increasing go together, negative and decreasing go together. And the rate of change is increasing or decreasing. Remember, that's asking about the concavity. Is it concave up or concave down? This one's concave down, which means our rate of change is decreasing. Think about our slopes here. This slope might be 4, and this slope might be 1. Those slopes are decreasing left to right. And then our graph of h. This function is all above the x-axis, so it is positive. Obviously, if we had arrows on the ends, it would probably cross. The graph is decreasing. It is going down, which means our rate of change is negative because all of our slopes are negative slopes. And the rate of change is, well, it's concave down, which means our rate of change is decreasing. If I think about what my slopes are here, this might be a slope of -1, while this might be a slope of -4, is getting more negative. So now you'll have a chance to practice some on your own.